why we get prepared.
Enjoy this. There's some sound. Now, there's no sound from me. Is there sound from Morgan? Can you talk, Morgan?
God in Fraser about starting on time.
Hold on.
Feel bad now.
This one? Okay, talk, Morgan.
Can you hear me now?
I sure can.
All right.
But
Some people say they can.
Yeah, but I
Yeah,
think
it seems like it's working now.
Yeah, but it appears that I'm a little quieter than you. Which
I have that problem a lot in life.
well, you know what? I now have a bundle of little boxes with little dials. So I can turn up various dials.
Who doesn't like a dashboard full of buttons?
I know. All right, let me turn this one up one little notch. Boop. There, now I'm a little louder compared to Morgan. One more time, Morgan.
What do you talk about?
There's massive sound lag. Yeah, well, that is the internet. And that can't be. We have no control over that.
Yeah, my internet's kind of sketchy today. I'll throw some stuff at the telephone poles and see if that helps.
I'm still quiet. Okay, I will. Let's go one more notch up. Although maybe we should just make Morgan more quiet, and maybe that's the solution. All right.
Ouch.
I've dialed up my gain a little bit, so everything's
all right. They say the lag's better now.
Yeah. Cool. Well, and we got like another second. We haven't heard Brad. Brad, can we hear you?
Test.
Yep. Perfect.
Okay.
Yeah, we got everybody here. All right. Well, before we get started, I'm going to say hi to a bunch of people. You've all had your chance. You knew what to do. If I don't say your name, you have only yourself to blame. Hello to Adam Synergy and Alex Desplund and Bill Hunsicker and Bill K and Blair Pigeon and Bobby Delavi and Borit Klankar and Brian Yoku and by GabTier11, CB Black, Carolyn B, Kathy M, Cecil Morgan, Chiragawasti, that's awesome. Citizen Gold, David Dunn, Eamon Fanton, Galaxia, Giselle Sabarin, Granville Wright, H. Roll, Hamad Wasim, Helgi Berkog, Henrik Bo Anderson, Holly Meyer, James Haney, John Gallant, John Suffield, Johnny Zed, that's the Canadian pronunciation, Kenneth Lepre, Leonard Lindstrom, Linda Sadek, Malcolm Bond, Momo Dario, Neil Geary, Peter Schultz, Peter Tort, Phil Berthus, Arnstro, Richard Jose Jacob, Rick Schwartz, Sergio Botero, Thomas Traniker, Tony Raggett, Vanilla JavaScript, Video Universe, William Vandebeek, William Bacon, and Zach Cody. Hey, everybody. Welcome to the Weekly Space Hangout. We'll get started in a second. Before we do, I got to say, did you... the BBC just did a documentary about Mars, and they put up my name right at the beginning. They had the 3-minute mark of this. Should we go to Mars? There's a quote from me in it. So if you haven't already seen it, it's in there.
Fancy. What is your quote?
Mars eats spacecraft for breakfast.
A dignified first appearance on the BBC.
Yeah. So I had the first quote, and then John Glenn had the one after me, which I think it's by far my favorite quote from John Glenn, which is, as his rocket was taking off, he was thinking about the fact that every single part of the rocket was supplied by the lowest bidder, which I think is awesome. All right. Well, I think everyone's in. They've all had a chance to sit down, and let's get this party started, y'all. All right. Brady Bunch view off. Morgan view on. All right. Here we go. And I know the chat is like wonky, and I don't know what to do. So I have to tweak it every week. Anyway. Hello and welcome to the Weekly Space Hangout for Friday, April 14th, 2017. I'm Fraser Cain, publisher of Universe Today. This week, we're going to be talking about life on Enceladus and Europa, maybe? A $500 billion plan to go to Mars, and the possibility that life came from asteroid strikes. Joining me this week, I can already see Morgan going, those were not the titles that I gave you, Fraser. Joining us this week, Morgan REHNBERG. Morgan.
Hey, Fraser. It's hard to believe that this is my 100th episode here.
100 episodes. That is awesome. And sadly, we're probably going to be one of the last few that you'll be joining us on, because you're going to go and
We'll fit a few more in.
You're going to get a real job, and yeah. And then we've got a special guest who is Bradley Peterson, who has already been on the show in the past. Bradley, welcome back to the Weekly Space Hangout.
Thanks. Glad to be here.
Now, for people who don't know who you are and what you do, can you give us the brief synopsis of what you do?
What do I do?
Yeah.
Okay. I'm a retired professor of astronomy from The Ohio State University, and I currently work at the Space Telescope Science Institute in Baltimore. And my main responsibility is that I'm chairing a science and technology definition team for a future space telescope that's generically known as the Large Ultraviolet, Optical, and Infrared Surveyor, which is a concept that we are trying to prepare for a new start in 2020.
Oh, and I cannot wait to talk about this telescope. And in addition, of course, you are on the science committee for NASA.
Yes, I chair the science committee for the NASA Advisory Council.
And so for people who aren't sort of familiar with the ins and outs of the NASA bureaucracy, I'm sure there's not very many of them, but for that occasional person who, what does this advisory committee do?
The NASA Advisory Council is NASA's highest level advisory committee that's made up of external people. So the advisory committee, or known as the NAC, advises the NASA administrator, mostly on policy issues. And then when we go one level down, there are the various associate administrators in their directorates, and one is the Science Mission Directorate, and the current associate administrator in the Science Mission Directorate is Thomas Zurbuchen, and the Science Committee advises him on various policy issues and communications and things like this. And then we go down even further, though we have a number of advisory committees that work with the individual directorates, which are astrophysics, earth science, planetary science, and heliophysics.
Right. And so for people who, people probably know that NASA creates lots of new kinds of telescopes, does a lot of research in astrophysics work, a lot of stuff coming out of, all those cool animations of black holes crashing into each other and things like that. And so there is this long process that scientists get together, they define the new kinds of research questions that they're looking to ask, propose the kinds of observatories, instruments, telescopes, and then your group counsels NASA on which of these instruments, observatories would help push the science forward, right?
Well, we actually advise them more on not what they're going to do, but on how they're going to do it. What we're going to do is something that's done through a National Academy study. Once every decade, we have these decadal studies where a large number of people in the field get together and come to some sort of agreement about what the next decade is going to look like in astronomy. So this is the traditional way that we've always selected what we think of as our flagship missions. The decadal in 1972 recommended Hubble, and that finally launched in 1990. The decadal in 1982 recommended the Chandra X-ray Observatory, which launched in 1999. In 1991, recommended the Spitzer Space Telescope, and also Sophia, as two slightly smaller things. In 2001, it was JWST, which is going to be launched next year. And 2010, it was WFIRST, which is likely to be launched in 2025. So what we are doing right now is we're doing a mission study that will try to bring the science and technology to a sufficient level of maturity that this decadal survey by the National Academy will be able to say, yes, this is a mature concept. It's ready to really start putting money in it and try to get this thing launched in the 2030s.
All right, so let's talk specifically about this mission. So what's the title again of the mission?
Okay, the title is, it's a generic title, as is WFIRST, right? What WFIRST is a wide field infrared space telescope. They get real names when they get closer to launch. At NASA is actually studying 4 different mission concepts now, with the idea that we're going to, within the next 4 years, we're going to have these things developed to the point where at least one of them can be recommended to move forward. So the first, ours is the Large Ultraviolet Optical Infrared Surveyor. The second is the Habitable Planets Explorer, known as HABEX. There is also a Far Infrared Surveyor, which has been renamed as the Origin Space Telescope, and an X-ray Surveyor, which is known as LYNX. And these all came out of a astrophysics roadmap study in 2014. And ultimately, basically, all the science is going to get done in this eventually, but it's a question of which ones are going to be ready, are going to be mature for selection in the next decade or in 2020.
So with is it the LUVOIR? How do you say this new?
We say LUVOIR. It looks like a French name, and our joke is say it like a pirate. LUVOIR. So, anyhow, we're looking at a couple of different mission architectures. We've got our architecture A, which is our optimistic one, where it will require an SLS launch vehicle to lift this telescope into the Sun-Earth L2 point. And what we're looking at there is a 15-meter telescope that will be segmented like the James Webb Space Telescope is, and will fold up inside a fairing and then deploy upon launch, after launch.
So a 15-meter but ultraviolet telescope.
Yeah, it will go actually from the ultraviolet at about 1,000 angstroms through the near infrared at about 2.5 microns. In fact, it can go a little bit longer than that, but it won't be background limited because we're not going to cool this telescope. That's cooling the telescope like you do with JWST.
Right.
That's a price break point. Yeah.
Right, but I mean, people have been talking about the James Webb Space Telescope as the successor to the Hubble Space Telescope, and it's not really, right? The Hubble Space Telescope will go from the infrared through the visible spectrum into the ultraviolet and produce a whole spectrum that the James Webb just can't do. It's down in the infrared. It's going to blow our minds and take us to the edge of the observable universe and detect newly forming planets, but it is not going to really replace. It's not going to serve in exactly the same places that Hubble will. So, so talk about this telescope idea, and where does that fit into the constellation of spacecraft that are already out there?
Well, this is, I've heard it referred to as the Uber Hubble. That it's like Hubble. It's intended to cover much of the electromagnetic spectrum. It will have general purpose wide field imagers and spectrometers, and it will be serviceable and have a long life, multiple instruments that will be replaceable. And the idea is that we're looking for something that's going to last in space for 50 years.
That
and again, with upgrades and servicing by astronauts or robots.
So unlike James Webb, this will be a serviceable mission.
Congress has mandated that all future large space telescopes must be serviceable if practicable.
Now, can you just give us, I mean, you're calling this the Uber Hubble, but can you give us some sense of scale? I mean, the main mirror on Hubble is 1.2.
It's 2.4 meters.
2.4 meters, right.
Yes.
And so this one...
So this is 15.
15 meters. I mean, okay, 15 meters is bigger than any visible light telescope that exists on planet Earth right now, right?
That's correct, yes.
So now, of course, there's the Giant Magellan Telescope and the 30-meter telescope and stuff that's in the works. So I'm
European extremely large telescope.
Right. Yeah. But I mean, if you took, say, the Keck telescope, a 10-meter telescope, and put that in orbit, it would be a mind-bending step forward beyond the Hubble Space Telescope. I really feel like you're underselling this. I guess that's what I'm saying, is that you're really underselling the capability of this telescope. And
No, this telescope is going to be remarkable. What the key science that it's going to do, it's going to be able to do spectroscopy of planets in the habitable zone around nearby stars. And if you can do spectroscopy, you can characterize atmospheric composition, and you can find whether something is habitable or not, and in fact, maybe if something is actually inhabited. So this is unbelievable. This is an unbelievable capability. And what we have to do, one of the technical tricks that we have to do to make that observation, is that you have to suppress the starlight,
yes,
so that it doesn't overwhelm the light from the planet. And this requires a coronagraph that will suppress the starlight at a ratio of about 10 billion to 1. So that's one of the technological challenges. Another technological challenge is that this exposure time, this will have to be done over the exposure time of the experiment. So you have incredible constraints on the stability with which you can point. Now, we've actually started going through some of the technology, and we find that we could relax some of the requirements from what we thought it was going to be originally by using active support of the mirror, where the individual mirror segments can be controlled just like they are with segmented telescopes on the ground like Keck.
So let's talk a bit about the coronagraph then. You know, the kinds of coronagraphs that we've seen so far, this idea of like a star shade, something that flies out maybe 10,000 kilometers away from the telescope and blocks the light from the star, but allows a lot of the light from the planets that could be around it. Is this the kind of concept of coronagraph, or something that's actually built right into the telescope?
No, we are looking at something that's built right into the telescope. It's it's essentially the equivalent of sticking your thumb over the over the star so that you can see the nearby planet. It's a little more complicated than that, of course, because there's actually a diffraction that occurs around your thumb. So it's designed to take that out as well. So it's really quite a remarkable thing. Now, the star shade is a really cool idea, but a star shade is essentially a separate mission, because we're talking it's going to have to be hundreds or thousands of kilometers away, and it has to maintain its position to extremely high accuracy. So you've got formation flying of two individual spacecraft. And when you want to look at something that's in a star in another direction, you actually have to change the orbit of the star shade. So that becomes a mission in itself. So we're not looking at that for anything we're considering in the near term, but that's we certainly got that as a future add-on.
Right. Now, you can't see this, but I'm going to put up a picture of this isn't even the telescope, but this is the high definition space telescope, which I think you've replaced this concept. I just want to give people a sense of scale here, right? So here's the Hubble Space Telescope. Here's the much larger 6.5 meter James Webb Space Telescope. And here is the original proposal for the high definition space telescope, but it's going to be bigger than this. Like, this is a mere 11.7 meters. So add another ring around this.
Yeah, that's right. And if you want some concept of how big it actually is, if you take the solar panels off Hubble, you can fly Hubble through the center hole in LUVOIR.
And Hubble is like the size of a school bus.
School bus, yeah.
Yeah. That is just phenomenal. All right.
Well,
let's talk a bit about in addition to just like for example, a telescope this big has never been built here on Earth, so that's interesting that you want to then put something like that in space. So can you explain some of the technical challenges that have to be overcome to make this happen?
Well, the telescope has to be extremely stiff and correctable on orbit. So doing it with segments is something of a challenge, but it's a solved problem on the ground. And we've also solved it in space with James Webb, so it's got heritage. It will be much cheaper than James Webb as well, at least at that on a per segment basis, because the segments don't have to be made of beryllium and they don't have to be coated with gold. So we're looking at something that we think we can constrain the cost because we're not cooling the telescope. Then we've got the challenge of building instruments that can make the full use of this. And we're looking at huge arrays of CCD detectors in the focal plane. So the power requirements are going to be significant as well. then of course, then there's the issue of serviceability. So we're thinking about that too. We're thinking about, okay, this thing gets out to L2. How are you going to service it? Do you bring it back to Earth Moon L1? Do you go out there to L2? So these are things we're still working about. And we're even right now carrying as an option, it might make sense to consider assembling the telescope on orbit. And a number of reasons for that. One would be that the infrastructure may exist because we're looking at a deep space gateway that will be in cislunar space. The price you pay to go from Earth Moon L1, the balance point exactly between the Earth and the Moon, go to there from the Sun Earth L2, which is 1 million miles beyond the Moon. It turns out it's 1/10 of the delta V that it takes to go from the surface of the Earth to low Earth orbit.
Right.
So you put on one of these weak little ion engines, so you don't have huge accelerations, and you can make the telescope a little bit more fragile than you would if the whole thing as an entity has to survive launch. So this is something we're carrying as an option as well.
So, I mean, and being able to send humans up to say the L1 point or to the moon, I mean, that is the kind of capability that NASA needs to sort of develop over time. Like, that's the next logical step beyond orbiting around and around and around the Earth, is to start
exactly.
to do tasks that are in nearby orbit. So that sounds
right.
like a great place. And so you could theoretically, if we do have the capability with, say, the deep space, what's it, the new machine, the deep space
Gateway.
Deep Space Gateway, that you could have astronauts up there. They could be working on this telescope, fine-tuning it, tweaking it, install new instruments, making sure that things are aligned. Like with James Webb, I mean, you've got this sort of origami, this robot origami that's going to be happening as it floats out to the L2 point, and then everything has to unfold and unfurl precisely. And if it doesn't happen, then sorry, like,
it's a bad day.
Try again. But to know that you're going to have human beings there, and you're both giving human beings sort of a task that is not just orbiting around the Earth again and again, but actually constructing this telescope and helping with the maintenance and pushing human beings further out. I think this is, I mean, it's got my seal of approval.
Well, the people I've talked to in the manned program, the individuals, of course, there's no policy on this NASA-wide, but the individuals I've talked to about this, including astronauts, are really very enthusiastic about it. Some of the NASA's best publicity has been the Hubble servicing missions. Probably that's the best publicity they've gotten since Apollo.
Yeah.
And the more recent mission, in fact, the last one, SM4, captivated people because of the helmet cams. You were able to see what the astronauts saw and watch them do their jobs.
Yep.
And it left people riveted to their computer screens for most of a week.
Yeah. My dad calls them the floaters. So my dad says, "Oh, the floaters are back on." And so let's talk time frame. Where do we stand now? Here we are, sort of entering 2017. When can we potentially see this come together?
Well, I think the real key is getting it approved by NASA as a new start. And so that would require first the National Academy recommending it as its highest priority. So that would occur in about 2020. And then it would probably take a couple of years beyond that to really start to formulate what the mission plan was going to be. And we would be looking at a potential launch in the mid-2030s. So that was partly why I went through the list of flagships that have gone before, to emphasize how long it takes. It's typical time scale from selection to launch of a flagship mission is something like 20 years.
But I'm gonna guess that most people haven't even heard that of this plan, of this telescope, of this, of what the capabilities are. And so I really feel like over that time, we're going to get some more details. Things are going to sort of come together. Let's talk about launchers. Just got a question here from Arjun. Are they assuming there will be a NASA rocket big enough to launch it, or could it go on a SpaceX or another rocket? So what class of launcher is this going to require?
It's going to require a heavy lift vehicle. I mean, what we're baselining is the SLS Block 1B, which has a 8.4 meter fairing. It's possible that this could go in a Falcon Heavy. I think the area is more constrained. So we're looking at second architectures as well. We're looking at alternative, slightly smaller architectures, and we'll just have to see if they can do the science or not. That's really what the study is about over the next year or so. Is what aperture does it actually take to do the science that we need to do? So again, we're in that process right now, but it's going to take a large launch vehicle. Even if we do assembly, it may take 2-3 Falcons or something to get the materials in place. We're assuming it'll be built in big pieces that basically snap together.
Right, but it's essentially the International Space Station, but it's a telescope, and would follow a similar kind of construction path. That pieces will be brought up.
Yeah, we know how to do construction in space.
Yeah.
That's proven, and the ISS and the Hubble repairs have shown that we know how to do this, and we know that we can do it with robots, and we know that we can do it with humans, and both have their advantages and disadvantages. And we're thinking, well, we're just going to make the best of both worlds. Use the technology that's best for the problem that you're presented with.
That's gonna be good. I think I really get the impression that for a lot of people, they're looking for some task, some journey, some next big goal for NASA. And we're about to talk with Morgan about the $500 billion Mars plan, and that and that is a lot of things have to go right for that to continue forward. And I think that we know that NASA needs a next step, and I think this does it. So I've been griping about the terrestrial planet finder for about a decade now, close to a decade, or at least since its cancellation. And in that for me would have been the single most important instrument I think humanity could create, because it'd help us answer the most fundamental question that human beings can ask, which is, are we alone in the universe?
Yes. And LUVOIR is intended to take over the role of TPF.
So when this gets approved, I can then stop griping about and blaming people about the TPF and now look forward to the future of this.
Yes, that's right.
All right.
This will be bigger than TPF, and considerable improvement in that it will be a telescope for general astrophysics. We'll be able to do lots of different things with it. We will be able to look for habitable planets around nearby stars.
Now, one of the other things that's kind of interesting is right now the field of exoplanetary research, they use these techniques. They use the transit technique, they use the radial velocity technique, and they can use gravitational microlensing. Will this kind of let you brute force it and just like look at stars and go, are there planets there? Block out the star and go, yep, and then just start counting them up? Like, where will this be as a planet finder?
As a planet finder, we would do it by direct imaging, using the coronagraph, and that's the way we'd find them. We can also explore known planets. So, TRAPPIST-1 is going to get some attention. Right. That's pretty, for example. So, there are a variety of different ways that we can do this. But what we can really do is the direct imaging and spectroscopy. So it's more than identifying them, characterizing their orbits, characterizing their masses and size and bulk densities. This is another step further. This is actually characterizing the contents of their atmospheres.
Well, I think it was an absolute treat to have you join us today. Where can people sort of watch and see as this process unfurls? What is like the next big milestone that they should be watching for? The next big milestone is actually going to be this decadal selection that takes place in 2020. If you're interested in the progress that we're making on LUVOIR, I provided you with a link, and it should be on your main page to the LUVOIR study. It's at Goddard Space Flight Center is where we've got our. That's where we're
mainly doing the study, and that's the home for our website. And there's all the good stuff on the science and technology is there.
Yeah, if you Google search LUVOIR,
Yeah.
the mission pops up. And so in 2020, they're going to do the decadal. They're going to vote. They're going to make their recommendations on whether to move forward with this or some other,
or what to, yeah, what
or
they
some
want to
other
recommend.
observatory
Yeah,
concept.
what
Yeah.
it's so you want to select something that has uniformly pretty high technology readiness levels as they're defined by NASA.
Yeah.
So if you have too many ones that are at low levels and you need a lot of technical development, you're not going to get selected. So that's really what we're doing now. We're retiring risk. That's our main job.
Right.
Yeah.
I like that term. Well, absolutely fantastic to talk with you, and I hope that in 2020 this gets approved and we can have you back on and talk about what the next step is, and looking forward to this.
Thanks.
Mission
Well,
coming together.
we're doing everything we can. We have a 24-member science and technology definition team. These are some of the best people in the field, and I'm delighted to be the co-leader of this group. So we'll just keep it going.
Wonderful. Well, thank you so much for joining us on the Weekly Space Hangout this week.
Thank you. Thanks very much. We'll see you again soon, I hope.
All right. So before we move on, I've got a little bit of, let's see, I've got some, here we go. All right. So on Friday, May 12th, the Weekly Space Hangout will welcome authors Michael Summers and James Trefil to the show to discuss the new book, Exoplanets, Diamond Worlds, Super Earths, Pulsar Planets, and the New Search for Life Beyond Our Solar System. We're going to be giving away a couple of copies of the book, and so you need to go to giveaways at WSHcrew.space and with the subject exoplanets. So there's instructions here, and I'm sure there's instructions on the WSH crew.space website, so you can join the giveaway. And let me know if this is fun. And we kind of can get lots of stuff like this. So if you want to win prizes, we can organize this on a regular basis. I realize I'm going to be in Austin over that period. So, but I'm going to be trying to be hanging out with Brian Brushwood and crew, and so I should be able to get access to his studio and maybe do the. I haven't asked him yet, but I'm gonna see if I can get myself some internet while I'm down in Austin. So, there you go. So just remember, go to wshcrew.space and you can get more information about the giveaway and join the community and get into the chat, which is down here. So, all right, and remember, whenever anybody has written a new book, they're ready to be on publicity and they'll come on the show. So just keep that in mind because remember, you are all producers of the Weekly Space Hangout. And so if there's someone you want to bring on the show, wait for them to publish a book. That's the plan. All right. Morgan, it's just the Fraser and Morgan show again.
We got a lot to talk about today.
We do have a lot to talk about, so I don't think that we're going to have any problem staying busy with the news that we've got today. So let's do the big one, which is that we found European space whales.
If only.
If only.
But we have gotten a bunch of really exciting news about so-called ocean worlds this week from NASA. And ocean worlds are this category of objects in the solar system that have sort of come into vogue, I'd say, in the last decade or even less. And it's because of discoveries at Europa, discoveries at Enceladus, maybe even places like Titan and Pluto. And it's hard to remember, but 13 years ago when Cassini got to Saturn, we didn't know that Enceladus was interesting at all. It was just one of a number of small worlds that existed in orbit about Saturn. And then, of course, we discovered those beautiful geysers shooting liquid water out into space to create the E-ring. And we discovered all this heat under the surface of Enceladus that was powering those geysers. And just last year, we confirmed that there's an entire ocean underneath Enceladus that is global, not just local to the South Pole, where we see these geysers. And as the Cassini mission winds down this year, we've been flying by Enceladus to make sort of our last best observations. And we were able to float just within 50 kilometers of the plume recently. And what was discovered was that the plume contains not just water, but also pure hydrogen, what we call molecular hydrogen, because it's H2. It's one hydrogen atom bonded to another hydrogen atom. And this is really interesting because it's not the sort of thing that you might find or expect to find if you just had kind of a still quiescent body of water. But if you have a body of water that's in contact with a warm rock base, then the chemical reactions that drives can generate a lot of pure hydrogen. And so what this is telling us is that down at the bottom of the ocean on Enceladus, where the ocean comes into contact with the floor, that floor must be made of rock, not ice, and that boundary must be pretty hot. And in fact, it might look a lot like the hydrothermal vents that we see at the crust ocean boundary here on Earth. And that's really, really interesting because these hydrothermal vents are just teeming with life. And in fact, there's a lot of species of life that exist only in these hydrothermal vents, and they derive their energy from taking carbon dioxide out of the water and combining it with hydrogen. And that chemical reaction produces energy, and that energy is enough to sustain microorganisms. And so this is proving that all of the ingredients are there for Enceladus to have the capability of sustaining life.
Right.
Now, one thing that was pointed out this week is that when you see something like hydrogen gas floating up to the surface and out the plumes, that might be a pretty good indicator that there aren't a bunch of microbes sitting there and munching on it. Because if they were taking it in and using it, then it wouldn't be reaching the surface. But of course, we're only seen this hydrogen at one point coming out of one part of the moon, and so it's possible that elsewhere underneath the surface, the conditions are right that life could indeed be surviving.
Yeah, so just to sort of recap a little bit here, that those black smoking vents that are at the bottom of the ocean, they are covered in methanogens and various exothermophiles, and then they are the base of this enormous ecosystem of shrimp and fish and the whole place. And the amazing thing is that if the sun disappeared tomorrow and the Earth was just this cold ball floating in space, that life wouldn't care one iota. It would just keep rolling. That you would still get, that its base of energy is coming from the center of the Earth. It is coming from the molten core of the Earth, and so it's not concerned about sunlight the way that other life is. So as long as you've got the energy source, the water, and in this case you've got this hydrogen, you've got it's food for bacteria. It's all the pieces are there.
Right, and that's really important for these ocean worlds because they are buried under kilometers of ice, reflecting away the sort of meager rays of the sun that reach all the way out to Saturn. And so if life was to exist on Enceladus or on Europa for that matter, this is always how it was going to have to work. It was going to have an internal source of heat that was in contact with the body of water. But just because that's how it had to happen doesn't mean that would actually have been happening. And so now we're one step farther. Now, not only does it have had to happen that way, but it is happening that way. And that brings us one bit closer to the possibility of there actually being life under Enceladus.
That's just mind-bending. But then NASA actually made two announcements on their conference this week. There was a whole other announcement as well.
Yeah, that's right. Europa was in some ways sort of playing catch up with Enceladus. Europa is the original ocean world. We've known since the Galileo mission in the late 90s and early 2000s that Europa had a global ocean underneath its surface. And in fact, that ocean has so much water that it's probably twice as large as all the oceans and rivers and lakes on Earth combined. So we're talking about a truly tremendous amount of water. But unlike Enceladus, Galileo didn't see any evidence of plumes of water coming out of Europa and streaming out into space. And so that led to some questions about, well, is the ice crust really thick? Is the heat source insufficient? Just Europa started to seem like less of a sort of slam dunk case than what we've been building for the last decade at Enceladus.
But also,
but
that it didn't have it didn't clearly have those plumes. So even if there is more ice, I mean, you can imagine because of Jupiter's greater mass and the tidal forces going on, it could have much thicker water, but also a thicker ice sheet. I mean, the magic of Enceladus is that water is getting out into space, and you can go and fly through it and taste it, right?
Right, exactly. And so a few years ago, it was really big news when scientists using the Hubble Space Telescope announced that they had kind of a marginal detection of plumes off the surface of Europa. And that basically means that they detected a water signal sort of right where you'd expect the edge of the planet to be. And I talked to people who made those observations, and they sort of they qualified them. This was not a guaranteed discovery. And to sort of prove that, they have coming back and made observations again and again and again. And just recently, they detected that same water signature above the same piece of the surface of Europa. And now that you have these two is vastly more compelling than one.
Right.
And they were able to calculate that for these two to have randomly occurred at the same location would be, less than, one chance in 10,000.
Mm-hmm.
And that corresponds to 99.99% likelihood that Europa does actually have of plumes. And to sort of strengthen that even further, the location that they calculated that these plumes must be coming from matches up exactly with the location that Galileo observed a really warm part of Europa's crust. And that matches exactly with what we have learned from Enceladus. Enceladus has an extremely hot south pole. All of these plumes are coming out of its south pole. Galileo observed an extremely hot part of Europa, but couldn't see any plumes. But now we see those plumes, and again, corresponding to that same spot.
No,
and so this...
Oh,
go ahead.
finish up. I was just going
to say, so what this tells us is that at least some of the time, there are definitely plumes here. Now, Enceladus's plumes, we've observed sort of ebb and flow. And just in Enceladus's day-long orbit around Saturn, they can increase or decrease in strength by like a factor of 3. And so it's quite possible that the plumes on Europa maybe aren't always active. And when Galileo was looking, it didn't see them. Mm-hmm. But when Hubble has looked, sometimes it's seen them, sometimes it hasn't. And maybe they come and go over time.
Right. And fortunately, there is a mission in the works, the Europa Clipper, that's going to be going to Europa, probably launch in 2022, get there in 3 years, maybe get there by 2025 on an SLS, and then it's going to do like 45 flybys past Europa. It's going to find those plumes, find the sources, fly through the plumes, and it's going to have a much better suite of instruments to try and taste the water ice coming out of Europa.
Yeah, NASA made a pretty big gamble when it was picking the instruments for the Clipper, because it included some instruments whose sort of primary focus was to observe the plumes. At a time in which the existence of the plumes wasn't guaranteed.
Yeah.
And there was questions in the scientific community about, well, if we get there and we don't see plumes, have we just spent a bunch of our money building instruments that aren't that useful when we could have been including other things? But in this instance, the gamble paid off, and the Clipper is full steam ahead in design now, and will be able to study these plumes that we're now pretty sure exist.
Ricardo Jose Jacob asks a question, would the radiation from Jupiter be blocked by this ice on Europa, and I guess in Enceladus as well. Is that ice protection from the radiation?
It definitely is. I mean, water is an extremely effective protector against radiation. If you've ever gone inside, say, like an aquarium, and you'll notice you never have cell signal, and that's because water absorbs, electromagnetic radiation really effectively. And one of the sort of ideas that we have for getting astronauts safely back and forth to Mars is to surround them in their drinking water. Because that will absorb that radiation. And so until we know the thickness of the ice, we won't know exactly how much protection is being offered. Yeah. But it's a 100-kilometer deep ocean, we think. And so even if there's a lot of radiation at the top of that ocean, there's really no top and bottom in the sense that there's no sunlight at the top. In some ways, the bottom is the top because that's where the heat is. That's where the energy is. Right. And that's the part would be most protected from Jupiter's radiation.
Now, I've seen a couple of questions here. People talk about this, that hydrogen is the most common element in the universe. Why is it so surprising to find hydrogen?
Yeah, that's a very good question. And the answer is it's extremely light. And because of that, it tends to sort of escape. It even can sort of leak out of rocks or leak out of the ice. And just over billions of years, it just sort of floats away. It's the most common element in the universe, but it's vanishingly rare in Earth's atmosphere. And that's because it just gets lost to space. It also is very effective at bonding with other things. So you think of things like water or methane. These are combinations of carbon and hydrogen or oxygen and hydrogen. And so it's pretty rare to see molecular hydrogen, which is hydrogen bonded with another hydrogen. That often gets split up and then bonds with other things.
And so, like, the moment that hydrogen meets up with oxygen, as we've seen in the case of, I don't know, rockets, they bond together and you get water. Like, to have free hydrogen like this, you need some source that is generating the hydrogen and it's making it out. And that source has to be rocks, hot rocks at the bottom of the Enceladacean
seems reasonable enough
ocean. And so this is what makes this discovery so exciting. So give people some kind of some kind of context here. Like is there anything left apart from us actually finding life there? Are we done? Like, are all the conditions there? We're ready to go?
So one thing we don't know a lot about is the carbon content of the ocean under Enceladus, because carbon's the building block for all life that we know of here on Earth. And so even if it's full of food, if there's nothing there sort of to constitute the organisms, then it'll be difficult to create life as we know it. And this is an instance in which Europa is actually sort of seen as a better candidate, because Europa is adjacent to the volcanic moon of Io. And Io is just blasting the Jovian system full of ash, essentially, which is basically carbon. And if there are geysers on Europa, as we now think there are, those can go both ways. And that ash can filter down through these cracks into the ocean, just as vapor, water is coming out. And now you have water and carbon and a source of heat and probably hydrogen. And where that carbon would come from on Enceladus is less clear. Now there is a rocky sort of core to Enceladus, and rock is made up in part of carbon. And so it's not like Enceladus is devoid of it, but getting that sort of filtering through the ocean is something we don't know very much about. Right. And we might not be able to understand, carbon's heavy, so it doesn't tend to float out with the geysers. And so even if it's there, we might not see a lot of it.
Right. Man, this is crazy. And so will the Clipper have the capability to detect like actual life? I mean, it's going to have a lander that in theory they're going to drop it down near the plumes. Is it going to have the capability to confirm that if there is life there?
Probably not. Kind of like Curiosity, Clipper is designed to detect the presence of organic molecules. So it's going to be able to tell if there are hydrocarbons there, for example, or methane, for example.
Right.
But it's not going to be able to actually detect, organisms. And even a lander probably wouldn't be able to make that sort of observation. So we're sort of one step at a time. The next thing, just like with Curiosity on Mars, the next thing to do is to prove that the chemical composition of what we find on Europa is conducive to life. That's an easy problem. It's basic chemistry. Either there is carbon or there isn't.
Yeah.
Whether or not there's life is a much more challenging question, and one that we tried to answer on Mars with the Viking missions, and we learned that it's really difficult to do that.
All right, so let's move on. We've got a couple quick stories now. I mean, this is. I hope this will all keep you excited for the next week or so. But now let's ruin Sci-Fi Christmas and talk about the $500 billion plans to go to Mars.
Yeah, so back in the 1980s, NASA developed a large plan for sending humans to Mars under the administration of George H.W. Bush. And this mission basically called for building a giant spacecraft that would bring everything in the kitchen sink from Earth to Mars and serve as a base for the landing of astronauts on the surface of Mars. It was commonly referred to as the Battlestar Galactica plan, because it was going to be sort of one Uber ship. And while sort of a good idea in one sense, it just went down in flames because it was attached to a price tag of about $500 billion. And that naturally gave Congress conniptions, and the plan was shelved with really no second thoughts.
That's like 20 years of an enhanced NASA budget if they spent every penny just on Mars exploration for like one monster ship.
Yeah, it didn't seem very feasible. And so since then, NASA has focused sort of on a more Apollo-style program where you send sort of bare bones, stripped down spacecrafts that each accomplish a specific task. So maybe you land something that produces fuel out of the Martian atmosphere. Maybe you land something with supplies. Maybe you land something with humans on board. And you can launch all of these things independently, send them up. It's supposed to be a lot cheaper. The bad news is that it might not actually be a lot cheaper. NASA's been really notable about not trying to talk about the cost of these things. And this drew criticism from their own Inspector General, which is an official in the government whose job is basically to sort of oversee a particular government agency and make sure they're doing the right thing. And the Inspector General for NASA criticized the agency for basically refusing to talk about the cost of things and sort of hiding that from the decision makers like the president and Congress and private industry. And they went through and sort of costed out their own estimate for what NASA has kind of proposed to do. And this was what they sort of called the most austere plan that they envisioned.
This is it on the cheap.
Yeah, exactly. This doesn't have things like the Deep Space Gateway. It doesn't have things like trying to develop the technology to make your own fuel on the surface of Mars.
Right. And
when they broke the calculator out and totaled this all up, the number that they got was $450 billion.
That's the same price.
And turns out it's about the same price. And that even included assuming things like we'll ditch the ISS in 2024, while NASA has sort of already committed to holding on through 2028. And the pieces that they were envisioning for this Mars trip were a landing on the moon Phobos in 2033, a 1 month stay on the surface in 2037, and then year-long stays on the surface in 2041 and 2046.
They could probably stay in the SpaceX hotel by 2046.
Yeah, that might very well be the case. And all of this was assuming that they could launch these things on SLS, the Space Launch System. And some of these pieces would take as many as 11 SLS launches at well over $1 billion per launch. And the IG also criticized NASA's timeline for the SLS, saying it was very unlikely that they would be on schedule for their launches in 2018 and 2020. And since SLS sort of forms the backbone of this whole plan, uncertainty in the rocket schedule breeds uncertainty in the overall Mars strategy.
So, man, okay. So how do we feel about this?
So I think that, in some ways it's good to be realistic about the cost of something like this. And you're right. If NASA devoted its whole focus for decades, it wouldn't have enough money to do this. And this sort of puts in ink what we've known for a long time, which is that NASA needs a budget increase if we're going to go to Mars, and not a little one. And if it's easier to talk about it from saying, okay, NASA needs, $10 billion a year, that sounds like a manageable small number. But when you multiply that over decades, now this is looking all the way out into the mid 2040s, that really starts to add up. And what is sort of a piece here and a dollar there is hundreds of billions of dollars when you add it up over decades. And I also think that this casts some questions about SpaceX's assertions for how they can get to Mars, because I think they've demonstrated very effectively that they can work much faster and operate much less expensively than NASA can when developing things like the Falcon 9 or even the Falcon Heavy. But even if you imagine that SpaceX could do everything 10 times cheaper than NASA, then you're still talking about a price tag, in the range of $50 billion. Mm-hmm. And, that's a tremendous amount of money, and in excess of the numbers that Musk has been throwing around for these kinds of Mars trips, which he think could be done, for $10 billion or $20 billion. And so I think this tells us that we should ask SpaceX to be a little, I don't want to say more reasonable, but to sort of not be quite as optimistic about the way in which they're thinking about their costs, because it's unlikely that they're doing things, 100 times cheaper than what NASA is.
Well, and I think that, the part of the whole, well, I don't know if it's necessarily our complaint, but the big criticism of the SpaceX interplanetary transport system and that is like literally all that SpaceX is talking about is building a gigantic rocket, filling it with human beings and dumping them out on the surface of Mars. That there's no conversation whatsoever about like, what are these people going to eat and where are they going to live and how are they going to get their water and how are they going to breathe and how are they going to protect themselves from radiation and what happens when their iPhones break. And, there are just a mountain of tiny little details. And I think in this case, NASA is going the other route, and they are looking at thinking about the details and then trying to sort of bring those details together into a larger mission plan. So it could very well be that even if SpaceX doesn't get to the details of how all of those things I just mentioned, that someone's gonna have to, right? Or you're gonna just die choking on the surface of Mars when they open up the pod bay doors. And you're literally having to re-engineer almost every aspect of life, of your daily routine. Like everything that we think about and take for granted, someone needs to go and go, but like, yeah, but how will you be brushing your teeth in 38% gravity, So.
Yeah, it's a big challenge. And I think the message here is that it's important to be upfront and realistic about the costs. And so that, we as society can decide whether this is something that we want to invest our money in, or whether we think that there are more worthy things, scientific or otherwise, to do with $500 billion.
Yeah. And man. And so this, this isn't a surprise to me on what this price is. And my guess is it's probably a half of what the real price is. You say this is the austere version. People are going to want the real version, right? And that's going to be $1 trillion, 2 trillion. It's going to be a lot. That really, and there's no way that any government over the course, any one administration is going to be able to see this through over the course of the 20 years that it's going to take to get to that 2046, right? So wait, no, that's 30 years. 30 years to get to the 2046. That it's got to just be these incremental steps. It's just got to be step after step after step. That we're going to build a space station that sits up at the L1 point, and humans are going to be there for a little while, and that's more complicated than the International Space Station. And then they're going to land on the moon again, and then they're going to visit an asteroid, and just each step, like just pick a plan that's 10% harder, and eventually, hey, what do you know? You look down and you're on Mars.
Yeah, this is sort of tangential, but one of the solutions that has often been offered to the Fermi paradox, which is why aren't once a race becomes spacefaring, why aren't they everywhere? And one potential answer to that is that the costs of space travel are just vastly more than we understand and anticipate. And now it's talking about interstellar or intergalactic travel. But even within our own solar system, we might be fundamentally lowballing ourselves as to how difficult it is to take even these small steps, and therefore how expensive it is to make even these small incremental advances. Yep.
Let us move on. We've got just like a minute left. Can we give the really quick version of an asteroid strike being the source of RNA? Because it's such a cool concept.
Yeah, this is a really cool concept. It's an update of the sort of classic astrobiological experiment called the Miller-Urey experiment, which showed basically that lightning strikes in an atmosphere like we might have had on early Earth could generate the bases needed for RNA and thus also for DNA. And in the decades since that was done back in the 60s, we sort of changed our mind about what the atmosphere looked like. They assumed the atmosphere was extremely poor in oxygen. And today we think it was still probably poor in oxygen relative to what we see today, but it was overall pretty neutral. And when you have that kind of atmosphere, their lightning bolt theory just doesn't really work. But this group of researchers decided that there were other ways to generate tremendous amounts of energy really quickly. And one of them that the Earth was experiencing all the time early in its history were asteroid and comet impacts during the late heavy bombardment. And these are just pumping enormous amounts of energy into small concentrated areas. And so they built an atmosphere that matches sort of what we think the atmosphere of early Earth might have looked like based on our current understanding. And then they used a stupidly powerful laser to sort of simulate the shock waves that the impact would generate. And those shock waves basically put energy into the atmosphere and caused a bunch of chemical reactions to occur. And the result was all the bits of the RNA that you need for early life. And this just sort of comes back to this idea that there are, real natural explanations for how life could have arisen on Earth without the need for sort of external components, whether you're talking about God or whether you're talking about panspermia or something like that. Well, everything that we needed might very well have been on Earth, and the experiments just keep showing that.
Right, and that just keeps punting the question further back, right? Like if it's panspermia, where did that life get going, and where did that life get going? So I think we know that the early Earth was smacked by asteroids pretty soundly. So awesome. All right. Well, let's wrap things up. I know we're sort of like reached the end of our hour. Great stories, great guest. I bet this was the first time a lot of you heard about this new observatory, and I'm really excited about what happens next. So Morgan REHNBERG, where do people find out more?
Yeah, you can follow me on Twitter at Morgan REHNBERG. You can also check out my latest project, which is called Chart Your World. Go to chartyourworld.org or follow at Chart Your World on Twitter. And I'm taking important data sets for the world and making them easy to share and easy to understand.
That is very cool. Of course, I'm Fraser Cain. You can subscribe to this channel, like it, give it a thumbs up if you enjoyed it. And then one last reminder that Go to the wshcrew.space. There'll be instructions on joining the giveaway, so you can get a free copy of this book that we're going to be interviewing the authors of. And I'm sure someone will post some comment in the chat, but there you go. All right. Well, thanks, everyone. Thanks, of course, to the WSH crew for providing the community. Thanks to Morgan. Thanks to our guest. Thanks to everyone watching, and we'll see you all in 30 minutes if you want to come watch, no, 22 minutes if you want to come watch Astronomy Cast. Otherwise, we'll see you all next week. Hold on, people didn't see that. Hold on, people won't see you. There we go. Wave again. There we go. Awesome. See you later, everyone.